Salutations, mini mathematicians! Hope you're having a fabulous day. You're doing your best. You're being nice to everyone. You're getting outside. Weather's turned into gorgeous San Diego, so we're all happy to be here. I want to just thank you for all your hard work. You're doing such a great job. And let's get started. 7.1c, if you are a notebook person, linear and nonlinear functions. We're doing this on a printout or right on PDF. Purpose, we're going to determine if a representation of a function, meaning if I give you a table, a mapping, a graph, a geometric pattern, or an equation, is linear or nonlinear function. Is a linear or nonlinear function. Okay, let's get started. Okay. So we're going to be looking at some patterns, and we're going to be looking and seeing if they're linear or nonlinear. So at Complete Foods, a local grocery store, has hired two different companies to design a display for food items that are on sale each week. They currently have a display that is 6 boxes wide. And grocery displays are something that's near and dear to my heart and helps pay my bills because Mr. Barr used to be in charge of designing and putting in those big displays, like, at Super Bowl when they have all those cool Pepsi boxes and they look like something really cool. Maybe it's like a field goal or something. So I have been in many evenings discussions of like mathematical formulas of how big this display is and how much space they have, because the more cases that display is, the more he sells into the store and the more some commission that the Barr household gets. So if I would like a new pair of shoes, maybe I need to make a display with as many boxes as possible. So let's take a look. So obviously space is a variable here that is a constraint. So right now the display is 6 boxes wide. So they would like the center part of the display to be taller than the outside piece of the display to showcase their mega deal of the week. The following are the designs that two different companies submitted to Complete Foods using their current display as their starting point, because that's how much space they have. So here's design team 1, and we're asked to draw stage 4 of this design, really similar to what we looked at when we were looking at linear patterns back when we talked about linear equations. So that's helpful is kind of looking at from each stage to the next, how many blocks are added. So here from stage 1 to 2, 2 blocks, right? From stage 2 to 3, 2 more blocks are added. So to draw stage 4, I'm going to take stage 3, which is 1, 2, 3, 4, 5, 6 blocks on the base. So there's half, and I need to make 3 blocks on one side, 3 blocks on the other. My center section used to be 3 tall, so now it's going to be 4 tall. Explain your process. Constant rate of change. That kind of sounds like something we've talked about before. Constant rate of change. What does a constant rate of change typically mean? Constant rate of change of 2 blocks per stage. Okay, so number 2, can the relationship between stage number and number of boxes in a stage in this pattern be modeled by a linear function? So remember, linear functions have a constant rate of change. We're going to create a table, a graph, an equation to support our answer here. So if I look at the table of values for my stage number and my number of boxes, first stage, stage 1, stage 1 had 6 boxes. Stage 2 had 2 more. Gets you 8 boxes. I have this plus 2. Then the next stage we added 2 more to get 10. The next stage we added 2 more to get 12. And the next stage we added 2 more to get 14. Double check on stage 4 that we have 12 boxes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Hey, looks good. Okay, so is the relation a function based on the table of values? So we want to be aware of what the question is actually asking us here. It's asking us if the relationship is a function, not if the relationship is linear. So is this a function based on the table? Is the relationship a function based on the table? So, is this a function? Yes. Each input or stage number, each stage input has a unique number of, I guess we're calling them boxes. I was calling them blocks a second ago. Output. Is the relation linear based on the table? Well, remember what we looked at for a table to see a linear relation. To look at a table to see if it's a linear relationship, we look for a constant first difference. So as the change in x is changing by 1, if the change in y is constant, which it is, we know the relationship is linear. And this change in, or this difference in the y values is called a first difference. So yes, there is a constant first difference in the table. And that's going to be really important because as we start to look at different functions in this module, we might be looking at a second difference or a third difference depending on the type of function. So it's really exciting. It's something that in Math 1 you're going to explore more of. Okay, so let's take a look at a graph. Stage 0 has 0 boxes. We can say stage 1 has 6, stage 2 has 8. Oh, okay. Would we say stage 0 has 0 boxes? I guess because it's a linear relationship. Okay, so stage 3 has 10. We have a constant rate of change. Every one stage we go up 2 boxes. Notice this is going by 2s. And grab my straight edge. And notice we actually wouldn't have at stage 0, 0 boxes because we have a linear relationship. We have stage 0 is talking about that initial number of blocks at stage 0 or a b value in our equation, in slope-intercept form. So is this the relation of function based on the graph? Yes. No vertical line segments. If a vertical line did exist in the graph, that would mean that one input corresponds with 2 different outputs. And we see here that there are no vertical line segments. We can pass a vertical line through our graph and it does not intersect any place more than once at one time. Is a relationship linear based on the graph? Well, yes. Graph is a line. Okay. Equation. So what would the equation be for this relationship? The equation, since we can say B is number of boxes and S equals stage number, number of boxes at any stage number would be 2S because 2 is our constant rate of change, plus 4, because if we went back to stage 0, we went back 1, we have to go back 2 here, which would be 4. Remember, sometimes putting in 0 into our tables can be super helpful for us understanding these relationships a little better. Does the equation represent a linear relationship? Yes. In the form slope intercept form of a line y equals mx plus b. Cool. Justify that the pattern represents linear growth by using the model. So using the model, we can say that this is linear growth. Pattern grows in only one direction. Remember, linear means one dimension, just length, or just height, linear. So pattern grows in only one direction, height. One dimension, one direction. Linear, one dimension. Pattern grows in only one direction, height. Constant rate of change. Cool, let's keep going. Next, we're going to be looking at design team 2 for complete foods. So taking a look at design team 2, we have the current display, which starts with 6 boxes. And then we notice that to stage 2, we're adding 3. Interesting. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oh, we added more than just 3, you guys. What did we really do here? Okay, so it seems to me that we're adding a block on the end also, and these 3. Okay, so obviously we're going to be adding 4 then to each stage. I'll just draw it down here since my scribbles got in the way. 1, 2, 3, 4, 5, 6, plus 1 on the bottom and 3 on top. Oh, you guys, look at this. Ooh. Well, we have now 4 on top, which means we'd had to add another one here. And I guess we could color in this way or this one. So how many did we add from stage 2 to stage 3? 1, 2, 3, 4, 5, 6. Whoa, this is something we haven't seen before, you guys. This is not a constant rate of change. Okay, well, let's draw stage 4. We can do that. So before, it looks like we're always adding 1 more to the bottom. So wouldn't that kind of make it, what do you mean, like wider? Okay, so we're adding 1 more to the width and 1 more to the height and making all the levels even. So here we had 1, 2, 3, 4, 5, 6, 7, 8. So now we're going to need 9 on the bottom. 1, 2, 3, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we're still going to have just 2 on each end. And we're going to start building this column up. Before it was 3, so now it'll be 4. 1, 2. Maybe your drawing looks better than mine. So we're adding 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's just explain our process with words right now. We are always adding 1 more to the height and 1 more to the width with making a box in the center. Okay, that makes sense. 1 more layer of height and 1 more layer of width. Okay. So, can the relationship between stage number and number of boxes in a stage in this pattern be modeled by a linear function? Complete a table and graph to support your answer. Let's take a look at this table of values. So we're going to have stage 1, 2, 3, 4, 5, and 6. Stage 1, of course, we started with 6 boxes. Stage 2, we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes. Okay. Then we had to add more. And stage 3, we had 6 more, so 16. And then stage 4, we had 8 more, so that's 24. So that's stage 5. Stage 5, how many boxes are going to be in stage 5? Well, we're going to be adding another height. So that's another 1, 2, 3, 4, 5. But then it's going to be another width. So that's 6, 7, 8, 9, 10. So plus another 10. And that's going to get me 34. And then to get to stage 6, again, we're going to have to add a whole nother row. So before that was 1, 2, 3, 4, 5, 6. So we're adding another 6 on top of that, plus one more 7, plus 8, 9, 10, 11, 12 to get me to 46. Okay, so let's look at our change in X and change in Y. So from 6 to 10, and remember this will show our first difference. From 6 to 10, we added 4. From 10 to 16, we added 6. From 16 to 24, we added 8. From 24 to 34, we added 10. And from 34 to 46, we added 12. So notice we do not have a constant first difference. So is this relation linear? No. Okay. So let's take a look at these next two questions. Is the relation a function based on the table of values? Yes. Each stage, your input has a unique number of boxes. Your output. Could also say, given the stage number, you can determine the unique number of boxes for that stage number. Unique meaning it's not unique meaning no other stage number has that number of boxes. It just means unique meaning that stage number doesn't have another number of boxes other than the one given. So taking a look here, is the relationship linear? No, this isn't linear. Relationship's not linear, but it is a function. The function is nonlinear. No, nonlinear. The table does not have a constant first difference. Okay, but I want to talk about in the table something that you're going to be looking at next year. So I'm going to have another color, and I want to look at the differences in the first differences. Okay, so how do you go from 4 to 6? Add 2. How do you go from 6 to 8? Add 2. Oh, I like this, okay. How do you go from 8 to 10? Add 2. And 10 to 12? Add 2. This is constant. There's a pattern. This is important. So this isn't your first difference. Obviously, this was our first difference. It was the differences in the Y values the first time. So this is called your second difference. Very original, I know. So this is your second difference. And notice for this type of relationship, your second difference is constant. It's the same. And that's really important for what type of function this is going to be. So let's take a look at this graph. So at 1, we have 6, about there. 2, we have 10. Notice this goes 4, 8. So these are going by 4. So if I only wanted to go up 2, I'm only going to go up there. 3 is 16. 4 is 24. 5 is 34, so 32. 36, so right there. And 6 be zoop, all the way up to 46. Wow. Okay, so if I wanted to kind of connect these data points, I'm going to start to see something that's a curve. So is this relation a function based on the graph? So if I want to know if something is a function on a graph, I'm going to use the vertical line test, which means if I run a vertical line through my graph, as long as it only intersects once and only once at any one time, we have a function, meaning we don't have any vertical segments that we can create in our graph, in our function, in our relationship. So this is a function, yes. No vertical lines. We can also say passes vertical. Why did I not spell that right? Vertical. Vertical line test. The VLT. Okay, is the relation linear based on the graph? No. The points do not fall on a line. Say the graph is curved if you wanted to. So justify this pattern does not represent linear growth by looking at the model. So notice looking at this model, we're not just growing in one dimension. We're growing out and up. We're growing in 2 dimensions here. So the model grows in 2 directions. Think about it as 2 dimensions if you wanted to. At the same time, or you can use the word simultaneously. We're getting wider and taller simultaneously. Okay, so now that you've noticed a relationship that is linear and a relationship that is nonlinear, we're going to be continuing looking at a real world situation with my friend Owen. So my little friend Owen, he is a handful for his mom. And so we have been trying to get Owen to be a little more responsible. And so we thought he's definitely old enough now to be making his bed. We told Owen, we'll give you a quarter. So now Owen, he is a little bit of a entrepreneur, maybe a little bit too smart for his own good sometimes. He kind of knows a quarter isn't very much money. So he kind of struck us this deal because we all know it's pretty easy to make your bed 1 day, 2 days, but it's a lot harder to make it like 3 days in a row or 4 days in a row. So let's see how Owen struck this deal with us. Owen earns quarters each day that he makes his bed in the morning. On the first day, Owen's mom gives him 2 quarters. On the second day, Owen's mom gives him 4 quarters. On the third day, he receives 6 quarters and 8 quarters on the 4th day. Because making your bed for 4 days in a row consecutively is kind of tough. Owen makes his bed every day, all those 4 days, and this pattern will continue. The model shows how many quarters Owen earns each day. Each box represents 1 quarter. And consider a relationship between the number of quarters received on a given day and the day number. So we want to know just about the number of quarters that Owen's receiving that day, not the total number of quarters that he has stashed away. So what's the independent variable and what's the dependent variable? So what depends on what? The number of quarters he receives depends on the day number that he's been making his bed. So independent is the day number, and dependent is the number of quarters given on that day. Okay, is this data linear? Well, let's see if there's a constant rate of change. Day 1 to day 2, 2 more quarters given. Day 2 to day 3, 2 more quarters given. Day 3 to day 4, 2 more quarters given. So yes, this data is linear. There is a constant rate of change, 2 quarters per day, and the pattern grows in one direction, one dimension. Okay, so define your variables and write an equation to model the relationship between the number of quarters received and the day number. Notice this is the number of quarters received, not the total number of quarters that he still has. Okay, so I'm going to say D is the day number. I find it a lot more useful to use variables that represent the situation instead of just always using X and Y. And I'm going to use Q for number of quarters earned that day. So number of quarters earned that day is 2D, and we can double check that. 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8. Perfect, looks good. Okay, so now we're going to consider the relationship between the total number of quarters that Owen has earned and the day number. So remember, this is the total number that Owen has squirreled away. So to do that, we're going to complete the table of values. So day 1, the number of quarters that he gets added that day are 2, meaning he has a total of 2 quarters. So day number 2, he gets 4 quarters added to his stash. So what's the total number of quarters that Owen has right now? 6. Getting richer. Then on day 3, he gets 6 quarters added. Day 4, he's going to increase his value of quarters by 8. And day 5, he's going to increase his value of quarters by 10 more. So that means he's going to have 12, 20, and 30 quarters total. Okay, so is this data linear? Let's see if there's a constant first difference. We can think about this as X and that Y if we wanted to. So here from 2 to 6, I'm adding 4, adding 6, adding 8, and adding 10. So if I take a look at the first difference, I notice it's not constant. So here, is this data linear? No. There is not a constant first difference in the table. We could also explain this by saying there's not a constant rate of change. Cool. So again, for this first part, this relationship, our relationship is a linear function, but here our relationship is a nonlinear function. Okay, let's look at our last example. You could finish number 8 and then pause the video, finish number 8, and then we'll go over it together, or you can just work through it with me. So your choice. Carbon-14 has a half-life of 5,730 years. So everything in the whole entire world is made of carbon. And one way that we can figure out how old super old things are, like bones they find or important documents, fossils, one way we can figure out how old something is by carbon dating. And if it has a half-life, it means that every 5,730 years, the amount of carbon there is going to decrease by a half. So the table shows the amount of carbon-14 that will remain after a given number of years. Consider the relationship between the number of years and the amount of carbon-14 remaining. Okay, so what is the independent variable and what's the dependent variable? Well, what depends on what? The amount of carbon-14 remaining depends on the number of years. So the independent is the number of years, and the dependent is the amount of carbon-14 remaining. Obviously, there's a lot of different types of carbon, so we're just testing carbon-14 here. Feel free to go bug your science teacher more about carbon dating. I'm sure they can give you some great information. You can tell them this sparse thing, that's fine. So let's take a look. Is this data linear? Well, that's the big question. So let's see if we have a constant rate of change. Notice for this number of years, we're always going up by 5,730. So for this rate of change, we can look to see if we have a constant difference in our dependent variable here. 8 to 4, we add 4. Subtract 4. 4 to 2, we subtract 2. Well, that makes sense, because if you have a half-life and half the amount decreases, you're never going to get to 0, first of all. You're always going to have half of what there was before, right? So if you always have half of what there was before, half of a bigger number is going to be less. Half of a bigger number is going to be greater than half of its half, because it gets smaller. From here, we're going to subtract 1. And from here, we're going to subtract a half. So is this data linear? No, this data is not linear. There is no constant rate of change. The table does not have a constant first difference. Good. Awesome job, you guys. I hope you enjoyed our 7.1c lesson, just exploring a little bit more about functions. And are all functions linear? No. And are all linear relationship functions? Well, no, because remember, it could be a vertical line. So thank you very much for your time. I hope you have a fabulous day. Do your best. Be nice to everyone. And I'll see you next time. Video bar.